So now we are going to dive into a bunch of different optimizations, try and understand these. Again, anybody who's skimmed through a course on compilers, this will all be old hat, but I'm just going to go through it anyway, right. Many of these optimizations, as you will see, are obvious and intuitive, but the point is, again, it's not that you want a human being to actually be doing all of them. A compiler, a program should be able to do them automatically, right. So many of them have been designed with that in mind, and that's why some things that you would think are very obvious are still put down as being a big deal. Okay, this is an example, right. Supposing you have a code where you say x is equal to 3 plus 5, right. There are two parts to how a program gets executed. The first is the compile time, the second is the run time, right. Compile time happens typically only once, run time for most programs happens many times. You are going to run the same program many times after compiling it. Okay. In the case of hardware, once you have created the hardware, you will then use it a large number of times, but the compilation process happens only once. So typically what is considered a good idea is spend more time during compilation, but reduce the runtime. This is an example where you can do that, right. X is equal to 3 plus 5. Why should I do this at runtime? I don't need to actually do an addition at runtime. I can straight away replace this instruction with x is equal to 8 at compilation time. So the first question you might ask is, why would I ever write code like this, 3 plus 5? Ideally you shouldn't, but what if 5 was a macro, some kind of a hash define that you did not actually know while writing your code, or at least you wanted to keep it in such a way that it could be modified by someone if required, right. Let us say that you are trying to put together the size of the frame required for a communication packet. It consists of many components. One of them is preamble size, some number of symbols to be sent out as pilots, the number of symbols that are incorporated in one packet of data, and the number of packets themselves. Okay. Now you are not going to be changing those at runtime, but you do want the flexibility of being able to change them at least at compilation time to target a different piece of hardware. Okay. Which means the compiler can then reduce all of that to a single number and use it from there onwards. This simple, fairly obvious thing is called constant folding. Okay. Offshoot of that is what we would call constant propagation. Here what I can do is I can now replace x, because I know that when I reach this instruction y is equal to x plus 4, because of the way that instructions are executed, right, the semantics of the C programming language, y is equal to x plus 4 is going to be executed immediately after x is equal to 3 plus 5, which means when I reach y is equal to x plus 4, x must have the value 3 plus 5, that is 8. Okay. So I can propagate this value in here 8, and then again do a constant folding and finally end up with y is equal to 12, and straight away done. So this is propagate then fold. Okay. Like I said, fairly intuitive and obvious. The good thing about it is this can be done automatically by compilers. It's not something that you need to sit around doing manually. So in other words, the point over here that I am trying to make is, do not try to do these kind of optimizations on your own. Use macros, use hash defines wherever possible, so that you can change things in one place and have it reflect throughout your code, right. The compiler will be able to take care of all of those and replace them with appropriate constants. On the other hand, if this was something like, instead of 3 plus 5, if this was two variables and they were assigned values, that makes it a bit more tricky, because then the compiler cannot easily tell that they are not going to change their value, and it cannot replace them with constants, not always at least. There is sort of growing from there, the next thing that we can come up with is this idea of common subexpression elimination. A good example of that would be something like what we see over here, right. Again, something which could easily come up in a communication system. What's the common subexpression, right? This part over here, 2 pi fcn, right. Strictly speaking, this first portion, this is actually constant folding. right? But what is more important after that is the fact that I can then use that folded constant depending on whether fc was a hash define or a variable, right? Now I would get different values. If fc was a variable, this now is no longer a constant but is something that I can compute ahead of time, right? I can basically call it wc or something like that, omega c. Right, in which case I could then write it as cos of wc into n sine of wc into n. In fact, I can go one step further and basically say that this itself is a common subexpression and call this as some Tn is equal to wc into n, so that I basically get cos of Tn sine of Tn. Right? Why look at it in two stages like this? Because if the code that I was actually dealing with was something like this, for I is equal to 1 to 1000, y of I equals x of I into cos of 2 pi fi plus z of I into sine of 2 pi fi, right? This 2 pi f is a constant independent of the loop, but 2 pi fi is constant only for this expression. Okay? So I could do it in two steps like this. I could basically create one constant k1 equals 2 pi f and then do k2 equals k1 into I and replace this with y of I equals x of I into cos of k1 plus z of I into sine of k1, sorry k2. Right? So you see what's happening over here. If I had not done this step, k1 equals 2 pi f, I would then still have to do 2 into pi into f over here, which would happen 1000 times inside the loop, unnecessary multiplication. Okay? I can replace that with one multiplication which goes outside and then do it internally. Okay? So this idea of finding common subexpressions is a very powerful optimization. Again, it is something that compilers are usually quite good at. Okay? Many of these cases the compiler would do a fairly good job of finding those common cases and removing them. Having said that, you will find while going through the synthesis process in Vivado that there can be cases where, by keeping this in mind, that you can actually reduce certain computations, you might find that you are actually able to get better performance if you rewrite your code to do some kind of elimination in this way. Okay? Now one interesting thing, it's called dead code elimination. Okay? So let's look at this piece of code and find out what the different instructions are finally going to do. I want to find out which are the instructions over here that have no impact whatsoever on the final output. Okay? So as I go through the compiler, let's look at this one first. It's just a declaration, I can't really say anything about it. Next instruction, I is equal to 1, then j is equal to 2. Now I is equal to 3, which basically means that any previous assignment to I is redundant. So I can go back and mark this as dead code. Okay? Next instruction, j is equal to I plus 4, overwrites the previous assignment to j, which was 2. That is also dead code. Okay? Return I. At this point, what happens? The assignment to j also becomes dead because I am not using it. What about the instructions after that? Not reachable. Okay? So this code could easily have been, I could also have in other words completely eliminated j itself, the declaration of j. So I could have converted this to just int I is equal to 3, return I, which if I do some constant propagation basically just converts into one step, return 3. Right? So the most obvious question that comes up when I show you a piece of code like this is, Why would anyone ever write code like this? And yes, the answer is you are not likely to, okay, but it can come up as a result of certain other kinds of optimizations that the compiler has applied, okay. So what happens is some optimizations, some kind of constant propagation, some movement of code around and so on, can result in a case where some code that you have written actually can be eliminated as dead code. An extreme example of that, which is something that you might very well encounter if you try doing something like, writing a small piece of code to find out the effect of, or rather how quickly does a particular operation take place in hardware or even in software, right. An example of that is, supposing I wanted to write a code to find out what is the time required for performing one addition in software, right. One way that I could do this would basically be to have one function that basically says void add, and which basically says for I is equal to 1 to, let us say 10,000, some large number, I will declare some sum is equal to 0 and then just say sum plus equal to I, some constant value, okay. And what I do is I then call this function, I start a timing factor over here, call add and stop, right. In other words, the delta time that I find over here should give me the time required for 10,000 addition operations, and by dividing by 10,000 I can get the average time required for one addition. The problem is the compiler will take a look at this entire code, try to figure out what's happening over here. I am calling this function add, but what happens as a result of add? Nothing. I am not printing anything out, I am not changing a value that is seen by the main function. So for all practical purposes, even if I don't do anything in add, it will actually give me the exact same output. This is an example of dead code, the whole thing will just get optimized away, right. And especially while writing hardware or hardware test benches, there could be situations where if you are not careful, you can end up with a scenario where your entire module has got optimized away because you did not use the outputs that were being generated, okay. Using the outputs basically means some side effect, print out a value, change some global variable, change something which the compiler cannot automatically assume is going to be part of the actual output and therefore can just be optimized away, okay. So dead code elimination usually doesn't occur by itself, but comes up very often as a side effect of other kinds of changes or tests that you are trying to do. Code hoisting is actually related to that sub-expression elimination that I spoke about earlier, right. The idea is very simple. If I write the code like this, what will end up happening? How many additions will be performed? This will basically do 100 addition operations. But if I rewrite it like this, this becomes one addition operation, right. So in other words, this is effectively common sub-expressions across iterations. It is not that you actually have a separate common sub-expression in different parts of your code, but across iterations of some for loop, there are common sub-expressions that could then be extracted out as a common element over there. This is called code hoisting because you are basically taking something that is present in the code and pulling it up out of the code. Strength reduction, right. This is another sort of class of optimizations rather than a specific optimization by itself. All that it says is, can you reduce the complexity of a certain kind of operation, right. What that means basically is, for example, how would you, is there any other way you can compute y into 4? You could add 4 times, but unless the processor that you are dealing with is something really old which does not have a multiplier at all, it is very likely that 4 additions is more expensive than a multiplication, right. Or you could do shift left by 2, assuming that y is an integer and so on, right. So this operation in most processors and definitely in hardware, right, the shifting is less expensive than multiplication. In hardware, it's obvious. The shifting is essentially there's no hardware at all involved over there. It's just a case of how you look at the wires, whereas the multiplication actually requires a hardware multiplier to be put in there and all the associated logic with that. So this is an example where you have taken an operation and replaced it with something that is easier to implement. Similarly, division by 8, right, this could be right shift by 3, okay, again assuming that t is an integer. Okay. Multiplication by 15, what could you do here? 16 minus 1. Okay. So you could write this as q left shift 4 minus q, well, minus q. Okay. Now it's a bit more tricky. It's no longer so obvious that this is actually better than multiplication, and in fact what you will find is on most modern processors, right, definitely any Intel or AMD processor that's in a reasonably modern laptop or desktop, this instruction on the right, the shift and subtract, is going to take more time than the multiplication. Okay. But in hardware, the instruction on the right is still occupying far less logic than putting a full blown multiplier that is required by the left. Okay. A similar thing that can be done over here is, but a slightly more tricky thing, which is also related to another optimization we will look at later. Supposing you had something like this, right, you want to do, you have some int c equal to 7 and a for loop that basically says y of I is equal to c into I. Okay. What can you do over here? It's not very, both c and I are changing, right. So how would you go about, you can basically add the previous value, you keep track of a temporary value over here, right, and you can basically say y of I is equal to t, and then t is equal to t plus 7, right. So effectively what you are doing is you are changing the value that you are getting in here. So what is it? After all, that 7 is to be multiplied by the index, the loop index, right, but the loop index is a continuous, it's a so called induction variable, it is varying continuously 0, 1, 2, 3 and so on. So you can calculate its value by addition rather than actually explicitly doing a multiplication. Once again, this is a case where it's a slightly more complicated setup. It's no longer that you can just look at the code and straight away say strength reduction, but if you understand what is happening over there, you can translate this into a strength reduction transformation. Function inlining, right, in order to understand why this works, you have to look at it from 2 points of view, both from software as well as hardware, right. In the case of software, what will happen is, what happens when you call a function? It's basically going to be a branch instruction in the assembly language, right. So you have to save the present variables to stack, create new stack space for the new function that's going to be called, branch, and eventually there will also be a return from the branch. Okay. So in other words, if you had something very trivial like this, you are just multiplying or squaring a number, the overhead that is associated with all of these steps is almost certainly far more than the time required for just computing that value. Okay. But from the point of view of writing code, it is still cleaner to write code like this. If I can write a function square which will actually just return x into x, right, that's a nice way of doing it because I can understand what's happening. I could also have done this using a macro, right, a hash define, but in some cases macros are a bit clumsy, they are not exactly the equivalent of functions, right. There is a potential for things going wrong because they are just doing some pre-processing, they are not really doing compilation and no optimizations over there, right. What could be done instead is that the compiler basically says, look, the amount of code inside the function is so small that the effort involved in actually calling the function is more than that required for computing it, so I'll just skip that and return the value directly. Okay. In terms of hardware, a function will get translated into a module which will have a start signal a done signal, possibly some kind of a ready signal for handshaking, and data then needs to be transferred into it, and data needs to be transferred out of it. Okay? The moment you have a start signal and a done signal, it means you have a finite state machine. It means that multiple clock cycles are going to pass just for activating and terminating that function. Okay? So, if you actually have an explicit function call that is converted into a hardware module, it will mean so many more clock cycles. If that function call is somewhere inside a loop, that number of clock cycles get multiplied by the number of times that loop is going to execute. Okay? So, in both cases, if your function is relatively small, inlining can be a useful thing to do. On the other hand, blindly inlining everything is also a bad idea, because it actually will end up bloating your code. It will make it much larger than it needs to be, because every time that you have this f of x, it will be replaced by x into x. Okay? In this case, of course, it is probably just as well to do this, but if your code was bigger, if your function call was bigger, every time you had f of x, it would replace it with a large piece of code, completely increasing the size of what you have. In the case of hardware, just making it so large, making the intermediate netlist so large that it's very likely the compiler will just fail. It will run out of memory and not be able to synthesize what you are trying to do.